sorry about. Oh, but you need this.
Yeah.
And then I have to remember to stop recording.
Yeah. Thank you.
Thank you, Heitor.
Yeah.
Okay.
Thank you. Thank you for being here. Okay, so for you and for people who watch it later, let me do a quick recap from last time. So last time I showed, I didn't really derive, but I showed like some steps on the way to deriving the famous quadruple formula which was first derived by Einstein, which tells you the amount of energy that goes into gravitational waves in a situation where you have like some kind of confined region where you have a non-zero time-dependent energy momentum tensor, and now you want to know kind of what is the amount of energy that is lost into gravitational waves out of this region. And then there's a quadruple formula which tells you that energy loss per time is given by, this is Newton's constant, and then there's some kind of time average that doesn't really matter for us here. And then it's a third time derivative of the quadruple moment squared. So we take the time derivative of the quadruple moment squared, and the quadruple moment is given in terms of the energy momentum tensor of your source by, just for completeness, integral over the volume of this space, and then over the zero component of the energy momentum tensor of your source that produces gravitational waves, and then times the spatial coordinates squared. Okay, so then starting from this formula, last time I derived using some very audacious order of magnitude estimates, I derived an estimate for the amount of energy density that goes into gravitational waves during a first order phase transition. And the formula I came up with was, let me put it here. So this was omega gravitational waves, which is the energy density in gravitational waves divided by the total energy density. So the fraction of the energy density that is in gravitational waves. And what we found is, let me first write this. Squared. So there was a dependence on the Wall velocity. So we just remind you, VW is the Wall velocity of the bubbles during the phase transition. Dependence on alpha. Alpha is given by the energy density that is released during the phase transition. This is kind of the energy density difference between the false and true vacuum divided by the total energy density in radiation during the phase transition. So it's an amount of kind of by how much I increase the energy density during the phase transition in thermal radiation. I mean, how much energy is released during the phase transition compared to what was already there in the thermal plasma. And then finally, beta over h, let's write it like this. Beta over hn, and hn here I this is really the Hubble rate at the nucleation temperature. The nucleation temperature was the temperature where the phase transition takes place. This we could derive by, it's the derivative of the bounce action with respect to the temperature times the temperature evaluated at the nucleation temperature. And this was an estimate for how fast the phase transition takes place compared to the Hubble rate. So if this is big, then the phase transition is fast compared to the Hubble rate. Okay, so this was this, and another important quantity is the frequency of the gravitational waves, and this is given by the time scale of the phase transition, which is beta. Okay, so this was like, this is at the time of the phase transition. Now we have to, because of course we are interested in these quantities today, so we have to redshift them to values today. And then I showed you last time, if you do that, you get a factor of, okay, there's 1.89 times 10 to the minus 5. H to the minus 2, h is little h is the Hubble rate in units of 100 kilometers per second per megaparsec, which is kind of 0.7. That's the latest, well, that's the current measurements. And then there's also a factor that doesn't really matter. It's like the number of degrees of freedom. Well, 100 over the number of degrees of freedom at nucleation to 1/3. I mean, for most theories, it's kind of 1. And the same here. So here you get the factor of Hn, Hubble rate at the nucleation temperature. And then redshifting it, you get 1.7 times 10 to the minus 5. Then a factor of Tn over 100 GeV. This is just chosen for convenience. There's again this factor G star n over 100 now to 1/6. And the whole thing is in units of hertz. Let me erase this here already. Okay, so this tells you kind of if you have a phase transition now, and this quantity in particular is very important if you want to know at which of the gravitational wave detectors are potentially sensitive. Then kind of you can plug in your values. And the most important quantity is nucleation temperature that really determines the frequency, right? So kind of the nucleation. Well, actually, okay, I should say. This is not, so, I mean, so in the case of a very supercooled phase transition, this is something I also mentioned, so if Tn is much less than, so supercooled, phase transition is defined by phase transition that happens at temperatures much less than the critical temperature. That's the temperature where the phase transition becomes energetically possible. And the phase transition happens at much lower temperatures. And then, as I also mentioned, then you have a phase of reheating afterwards to a temperature that I call the reheating temperature, which is roughly of order the critical temperature. And then actually what you have to use here is really the reheating temperature. So it should actually replace this. So
the power of G is 1/6.
Yeah, it's 1/6 exactly. But again, it doesn't really matter for. I mean, if you have a theory with like a vastly different number of degrees of freedom than in the Stern model you have 100, then that because of 1/6, it's very insensitive to that. So yeah, the really the important quantity here is this thing, like how it scales with like the reheating temperature.
Which
so.
is around TC.
And this is around, I mean, it can be, I guess, 1 or 2 orders of magnitude away, depending on your theory, but I mean, roughly around TC. So, yeah, and later I'll show an example. Like, but this tells you then, like, later I'll show how to which temperatures now the different experiments are sensitive to, right? So this is kind of what determines this. Okay. Okay, so this was kind of our rough order of magnitude estimate, and now, of course, people did more than that. So now there are some numerical simulations that allow you to extract the gravitational wave spectrum. And as I also mentioned in the beginning, there are two types of main sources for the gravitational waves in the phase transition. One is from bubble collisions. And the second one is from sound waves. So the bubbles kind of collide, and then afterward there's still like sound waves moving around the plasma. They can also collide, and they lead to the production of more gravitational waves. There was also a third source from turbulent processes, but I said that this is kind of smaller than the first two sources and also theoretically less well understood, so I will not talk about this. Okay, so then numerical simulations. And now let's first start with bubble collisions. So the first source. And this is from a paper by Stefan Huber and Thomas Konstantin. The archive number is this. This is quite old already, 2008. There is now also there are newer numerical simulations, but they are a little bit, you can think of them as kind of refined versions of what I show you now, the spectra of additional dependencies. And in order not to make things too complicated, I just wanted to show this simpler spectra here. So, and what actually one really the spectra really are. So this is the whole energy density in gravitational waves divided by the critical energy density. But now, of course, you want to know the frequency dependence. And so what these numerical simulations give you, it's called omega GW of f, of the frequency, which is just the derivative of this quantity here with respect to the log of the frequency.
So what is B again? So
And B is now for bubble collisions, so I put the B now to make clear that it's for the bubble collisions. And I pulled the h squared in front because it's kind of convenient to parameterize it like this. So, okay, so this is really like, whenever I write of f, then this is really this. It's like the spectral density of the spectrum. Okay, so now what the simulations give you is this, 10 to the minus 5. Okay, times 0.11. I just write all this down now. It's readable, but I'll say it. Okay, so this is, so now this is essentially, now you can compare with our estimate. So the beta of h dependence is the same. Also depends on alpha is the same. Kappa, I forgot kappa here. Kappa squared. Kappa is this efficiency factor that tells you by like how much energy actually goes into gravitational waves of the latent heat that is released. I will say a few things about this later. Okay, kind of the upshot is that it looks remarkably similar, I would say, especially if you look at the kind of dependence on the velocity here. It goes like the cube power. There's something in the denominator, but for practical purposes that doesn't have much of an influence because
frequency spectrum and denominator is
exactly. And so, of course, the part that we didn't have here is kind of now the frequency spectrum. So now let me plot this. So the broken power law. So this is now h squared GW as a function of the frequency. Okay, I'll give you the formula for the frequency in a second, but let me first plot the spectrum here because it's generic, right? There's the peak frequency, and the spectrum looks like this. So you have a broken power law, where here the slope is, didn't really plot it in the right way, 2.8. Right? So if f is much less than FGWB, that's kind of the peak frequency, then this term in the numerator dominates, so it goes up like 2.8. And then for very large f, you kind of have this piece in the denominator dominating, and it goes down like slope is -1 here. And okay, so it's interesting to see kind of the dependence on a few parameters. So first of all, you see that this arrow here means like the direction of growing quantities. So for growing alpha and wall velocity, kind of the spectrum goes up, right, because of this factor and this factor here. But not arbitrarily, because for alpha, very large alpha, this saturates to 1, and the wall velocity can also be at most be 1, right? Then it's relativistic. Another important quantity is beta over h. So if I raise beta over h, raising beta over h means making it faster, the phase transition. Then you see, because it goes like 1 over beta h, the spectrum goes down. And this I didn't show yet, so let me first, because now in order to understand why the error is not straight down, let me give you the formula for the peak frequency. So the peak frequency is given by 0.1 10 to the -5 hertz. Then depends on the wall velocity to the. No, sorry, this is the wrong formula. 1.65. 10 to the -5 hertz. 0.62. 1.8. Squared. H. Okay. So you see again, like kind of the dependence is the same that we got from our estimate on beta, the number of degrees of freedoms, and the reheating temperature. So I should just more generically write this as the reheating temperature. And now you see that kind of, so if I raise beta over h, the spectrum goes down, the amplitude goes down, and the peak frequency is shifted to the right. So this is why I plotted this kind of like this. And then the last important, and probably the most important parameter is the reheating temperature, and that tells you how the peak frequency shifts. Like, I mean, that really sets the scale of the peak frequency, right? So this will then determine so for a given reheating temperature or roughly critical temperature of your theory, this will determine which of the gravitational wave experiments are sensitive. Okay, so now let me also, for completeness, just give you the formula for sound waves. So now for sound wave collisions, and that's a paper by Hindmarsh and, well, it's Hindmarsh, Huber, Mukainen, and Ware. From 2015. And again, they are slightly newer results, but they have a bit more complicated dependence. They introduce essentially depend on extra parameters, so I wanted to keep it simple. So let me abbreviate this with sound waves. So it's again the frequency spectrum. Okay, it looks like this. So again, like the dependence. So now the dependence on beta over h is not, before it was beta over h squared, now it's just beta over h. This can be analytically understood. Also, this is due to the fact that the sound wave production, the production of gravitational waves from sound waves lasts longer. So it's enhanced by a factor of beta over h. This factor here, I'm not so sure. So why it's linear in the ball velocity and not cubic, but probably this can also be understood, but I don't know now how. Okay, and then the rest is again the same. And now the spectrum is again a broken power law with, so let's see, it goes for small frequencies, it goes like the third power. So now this would be, goes like power 3 here, slope 3, and then for very large frequencies goes down with -4. So it's a bit steeper. The final quantity is a peak frequency for this case. To the -5 Hertz. There's also dependence on the ball velocity here. Again, the same beta over h dependence that we had before. It's again linear in the reading temperature. That's the most important thing, the most important dependence. And the dependence on the degrees of freedom. Okay, so now you know how to calculate the spectra of produced gravitational waves and first order phase transitions. Now the next question is, how can we detect them? And I just want to briefly throw out some gravitational wave experiments that are either already running or are planned.
So just before I proceed, so the two contributions are comparable, right? They're not
Sorry. So I didn't. Yeah, I forgot to talk about this. So there are these efficiency factors. Kappa SW for the sound waves and kappa B, I call it, for the bubble wall collisions. And those now determine like how important one contribution is versus the other. And so the thing is that I also mentioned that for the Wall velocity there are two regimes. So one is in which the Wall velocity is non-runaway. So it can be relativistic, the Wall velocity can be very close to 1, but the gamma factor stays finite. The other option is that it's a runaway bubble, so that kind of the gamma factor just diverges, it goes to infinity. In the non-runaway regime, one can actually show that the sound wave collisions, that's the dominant contribution. The contribution from bubble collisions is very small, it's negligible. So in the non-runaway regime, you can forget about the bubble collision contribution, and you can just focus on this contribution here. In the runaway regime, in the other regime, you have a mix of the two that you have to. But as I also mentioned, the runaway regime is actually very difficult to reach. This was this vertical Moore criterion that I mentioned. So in most theories, you need extreme amounts of supercooling to reach the runaway regime. So that's why, for example, in the LISA review, in the latest update of the LISA review, cosmology or gravitational waves from phase transitions, they focus exclusively on this sound wave contribution because if you're interested, they have a short argument, like they calculate like which amounts of supercooling you need in theories to reach this runaway regime. So, and in this case, and this is also what I will assume later. So purely focus on the sound waves, and then in this case, you can estimate this kappa, and it's roughly, very roughly, kappa goes like alpha over. Well, actually, it's like some order 1 number plus some other order 1 number, root alpha plus alpha. So, and later we will be interested in, and this is actually, sorry, and then this is for relativistic velocities. For non-relativistic velocities, it's slightly different. But later we will be interested in the situation where the velocity of the walls is relativistic and alpha is very big, so then it's essentially 1. So you can use this formula for the sound waves. But there's a little bit, I mean, okay, one has to be a little bit careful because this numerical simulations actually, they are believed to be trustworthy only for alpha less than 0.1. But most people, I think, just are audacious and just extrapolate it to a much larger alpha. But there's some discussion in the literature about whether that's... Anyway, that's at least what I will assume, or I think the papers I will show later will have assumed. So, just briefly list a few gravitational wave experiments. That's probably very new for Ricardo.
Yeah, all particle physics, they call it experiments, but they're not, they're observations.
Yeah, I know. And I also actually tried to say observatory.
No, you wrote correctly, but I think...
No, but I think afterwards I said experiment. No, anyway. Yeah, but exactly, so they're not... So...
I mean, there's a difference, not because the sources, you cannot know what you want.
Yeah.
That makes the difference.
So I will... So first of all, there are ground-based interferometers, so ground-based observatories on our planet. And the most well-known one is LIGO. There are actually 2 observatories in the US. Then there's also very well-known, of course, Virgo. And now since, I think recently, right, Kaka also in Japan. Virgo in Italy and Kaka in Japan. So these are already running. And then there's, I think, planned also a LIGO in India. And if I'm not mistaken, that's supposed to be up and running in the late 2020s, is that right? Yeah. Okay, so this is kind of what we have already or we'll have very soon. And then there are a bit more futuristic proposals. The Einstein telescope, which will be the successor in Europe. To
Can we switch it off?
yeah, sure, sorry. Don't want to do this. And that would be in the 2030s. And then there's also, this would be the European version, European Observatory. There's also one proposal in the US, the Cosmic Explorer, also. And yeah, so later I'll show you, I mean, the most interesting information now is actually what kind of frequencies are they sensitive to and how sensitive are they, but later I'll show you plots where you can see this. So then you will also, they have different sensitivity curves for these experiments. So that's one reason why I all bring them up. So that was ground-based. Now, as you may have guessed, there's also something space-based. Since I talked about ground-based first. The space-based experiments, observatories. So these are also interferometers. Space-based interferometers. Again, the best known one, I think the most advanced. Is LISA, which is a collection of 3 satellites that is planned to be launched in the 2030s. And then there was 2 potential successors already. It's DSIGO, or like a slim-down version called PDSIGO, which is a Japanese proposal. That I think they also aim for the 2030s, which is for PDSIGO. And then there's a Big Bang Observatory, which is a bit further down the line in the 2040s.
There is also some Chinese project
Okay.
alongside the LISA. They are not as advanced as the LISA.
What's the name?
I don't remember it.
Okay.
But yeah, I mean they're less advertised because everything that comes from China is a bit more obscure.
It's changing, I would say, right?
Yeah,
so,
but it could
used
be,
to be maybe, but I mean,
it could be US propaganda,
Yeah.
I can look it up.
Okay, so the final, there's another type of observatories, and these are so-called pulsar timing arrays. And the way these work is they observe a large number of so-called millisecond pulsars, which are like pulsars with spinning periods for milliseconds. That's where the name comes from. And they have a very stable frequency, and so if a gravitational wave now passes through, they kind of slightly change the frequency of these millisecond pulsars, and then by observing them, and observing a lot of them, you can also use these observations as a gravitational wave observatory. And there is 3
Taiji. Chinese Taiji.
Taiji. Maybe there's a later I'll show a plot with like they have a lot more than this. Maybe it's also on there. Let's have a look. So it's a very busy plot. So there's Nanograph, and it's an American collaboration, I think. And by the way, they already have a hint about some signal, I think. There's a Parkes pulsar timing array. So these all use different radio telescopes. It's also running. And it's an European thing, the European pulsar timing array, which is mostly European radio telescopes. It's also running. And then there's something that will come up also in this decade. This is the so-called square kilometer array. This is now, actually this is an observatory. These were like collaborations. But in the plots that I will show, these are like, they use this label here for the, I guess this would be some kind of gravitational wave, some kind of pulsar timing array using this SKA. So anyway, so SKA, that's really the radio telescope in the square kilometer array, which has an effective area of 1 square kilometer. It's okay. So just remember these names because they will come up in a few minutes. Okay, so now that you know some experiments, now the question is how do we measure? I mean, how do we see if a gravitational wave signal is actually observable with these observatories? And for this, we need to talk about sensitivity curves. Sensitivity curves. And yeah, so something to note is that kind of the sensitivity of these gravitational wave observatories is limited by all kinds of noise sources. For example, for these interferometers, examples would be thermal noise and seismic noise, so some kind of movements of the Earth. Also the so-called shot noise, it's kind of the Poisson noise of the lasers. And yeah, essentially now you have to kind of compare your signal with these noise curves to know whether a signal is detectable or not. And for this, it's useful to kind of use some kind of equivalent noise energy spectrum.
But Sky is not taking data already, right? It's not taking data yet, Sky.
No, not yet. No, I think they're still building it.
So it's Australia.
But I mean, I think it's on track, right? So it's yeah, Australia and South Africa also have these two sites.
Yeah, there's some preliminary arrays. I think it's called Meerkat. That also does radio stuff. So this is radio.
Yeah. Okay, so for the sensitivity curves, what you do is you take, I mean, that's what the experiments give us, some kind of effective noise energy spectrum, energy density spectrum. I guess you can think of this as kind of the energy density that would give equivalent signal, energy density gravitational waves that would give equivalent signal as a noise, right? So this is just kind of repackaged into this form because it's convenient. And then once you have this quantity from the experiments, you can calculate the signal to noise ratio. And that is given by the following expression. So it's the square root of the observation time, and then you integrate over the frequencies. And what integrate is
The frequency cannot be negative.
yeah, you're right. I don't know, it's probably 0 here. Yeah. You integrate over the frequencies, and integrate over is the omega gravitational waves. That's the quantity that the numerical divided by this noise, Poynting noise, F squared. And then this has to be larger than some kind of threshold. But again, you get from the experiments, which is kind of a number between 1 and 10 roughly. So we calculate this. So you kind of take your spectrum, your noise spectrum, you calculate this quantity, and if it's larger than this as a threshold, then you know that your signal has a chance at least of being detectable compared to the noise. So, but now, it's not very convenient.
That's not how you do it, right, Ricardo? Because you have to estimate the number of, how to say, accidentals or something?
No, I mean, this is the output correlation. So you assume the noise is not correlated and it drops out.
Exactly.
So basically, this omega is already quadratic in the signal, right?
Yes.
So it's the output of the correlation. So you assume that the signal here is correlated with the signal there. Of course, not exactly the same because they see different direction in principle, but it's correlated in the way you know for any given direction. Whereas the noise, you assume it decorrelates. And now, the important thing is the rise in the square root of time. So since basically the signal to noise ratio square increases linearly with time. This is a very generic thing about correlation.
But I remember somehow that you also have to, you could estimate the background from data.
No, but this is stochastic. What
yeah, I'm talking about stochastic. And these are stochastic.
Sorry. We do it not present all the time.
I'm sorry.
Are present a specific amount of time. So we do coincidences slides.
Yeah, sorry.
This you don't do here because if you slide the signal, it's not supposed to change.
Of course.
Exactly.
So it's not, yeah, it's
No,
not
here basically you take the correlation as zero lag and basically you just add the lag which is due to the different direction. Different direction has different delay, of course, because of the direction.
Right.
You just add coherently this and it's done. You don't have any other, you just assume that the noise is correlated. Whereas for our case, you have this freedom of sliding and finding
You can open the door too. If you
sliding.
You can open the door.
Yeah, a little bit.
Yeah, so that's
Yeah,
stochastic.
put the in so it doesn't.
Exactly. So, yeah, so this is what stochastic gravitational is. So, okay, but what I wanted to get at now is that kind of, it's not very convenient to do that for every button. You can do it, of course, for every kind of spectrum you have, but it would be nice to have some kind of visual way of seeing if something is potentially detectable or not. And for this, one uses the so-called power law integrated sensitivity curves. This. So the idea is that you make the simplifying assumption that your spectrum is not a broken power law, but just a simple power law. So it has some amplitude and then some slope that you call gamma. And this is some reference frequency that you can just fix for a given experiment. Let's fix it to the peak sensitivity. So it's like kind of the frequency for which the noise spectrum is the smallest. So let me just plot this here in this example. H squared and noise. So typically this looks something like this. And now some kind of function that has a minimum somewhere. So that's kind of the around the frequency where you have the highest sensitivity. And well, so this is this curve. So now the idea is that you okay, let's fix this frequency, this doesn't matter, so let's fix this frequency just to this value here, say. And now you calculate for different slopes, gamma, you calculate the amplitude for which the signal is detectable. So you take this, you plug it in here, and you calculate the omega for which the signal is detectable. Right? So you if you have this is an example now, right, for such a power law.
So you have a to the plot in omega and gamma. You have a to the plot in omega gamma. I guess you will show us.
No, so I will not show. I will show. So okay, so you do this for a given gamma set. You vary the amplitude until this signal to noise ratio is above this threshold, so it's detectable, right? And now you do this for different gammas. So now you can, so now you vary gamma, so for a different gamma, you look like this, say, another gamma like this, another gamma like this. And what you then take is the envelope of all these different curves. So you get now a series of power laws that like wrap around this noise curve.
Would be similar to the omega noise then?
Yeah, similar but not exactly the same. I'll show you later. So it's a bit further down, right? So and what this now gives you is because the broken power laws for the omega GW, these are broken power laws, right? I mean, they are like locally well described by a power law, right? So you can just now you can take this sensitivity curve here, this power integrated sensitivity curve, and just compare it with your spectrum. And if the spectrum touches this power law integrated sensitivity curve, you have a good chance of detecting a signal. So this is the way these results and compared with sensitivity curves are presented in the community. So let me can I now show the plot?
Is it there?
What do I have to do now?
The password is written on the screen.
So can I Google? Just open the paper here one second.
But you have to see that, right? You have to project it.
Yes, I don't know how to.
I don't know how. I thought that you know how to do that now.
Now it's recording
It's
the
recording.
camera.
Can we just switch on the? Yeah, I don't know. If I'm gonna do it, but I can.
We can project, no? With this projector here?
Yeah.
With our
That's-
laptop?
Yeah.
Think that's possible?
Let's try. With my laptop or with this computer?
With your laptop. There was a cable. Is it okay?
No, it's possible. No, it's not giving me. Can we try it or what do we do?
I don't think we can project because now it's recording from this computer.
Yeah.
I mean, we can approach show us the plot.
Yeah, but now nobody can see it, right? So
Yeah, nobody can see, so...
Well, okay, you can kind of, then let me just do this. Because people, if they watch it, if anyone will watch it, they can just open the PDF on their computer. So let me just give you.
Maybe try to black out the high number.
Exactly. I had it on my computer, better prepared. Okay, so whoever is watching, we are looking at now. So we are looking at.
I never used this.
No.
But which software I use for recording?
It's software from SAIFR.
Okay, let me do this. So I'll just write, and then whoever's watching this can just. We're looking at figure 2 in 1811-11175.
So then you tell us what are P and I sensitivity curves. P and I sensitivity curves.
This exactly this, right? Exactly. So now
Power oil.
exactly. So now on the left plot on figure 2 you see the original density noise, energy density noise, right? For EPTA, now graph, star, ESA, BD side, or BBL, mansion telescope. For some reason they forgot about LIGO here.
Well, like it's too much high.
No, it's actually, it's not so bad actually.
So I think I'm -6, you're right. It's between -6 and -7.
Yeah, somehow, right? I don't understand why they forgot about it. Okay, so this was the left plot in figure 2, and then the right plot in figure 2 shows us the resulting power integrated sensitivity curves. And you see that kind of curves change a little bit.
What alpha do they correspond to?
What do you mean, what alpha?
I guess these lines, these are the ones which are detectable. So, but what is the alpha omega pair they correspond to? These which are detectable.
Well, I'll show you in a second. So
Okay.
we come to that. So, okay. So, and then in the middle you see kind of the spectra, some example spectra.
It's the noise spectrum.
No, these are kind of sensitivity curves, and these are now example spectra for gravitational.
Which like just graze the
Exactly. So now these are these dash curves in the right plot on figure 2, and now you see that now you can get. I mean, essentially, if they touch one of these polar integrated sensitivity curves, you have a good chance of detecting this. It's kind of the visual information in these curves, right? So, and LIGO has some kind of LIGO would be up here.
to order 1 to order higher than ED.
Yeah, exactly. So it's definitely. Okay, this was figure 2. Now let's go to figure 3. So figure 3 now is using the spectra for for the two cases. On the left-hand side is for runaway bubbles. This would be mostly. Yeah, this is the case where you have both bubble ball collisions and sound waves, and on the right column is non-runaway bubbles where you only have sound waves that contributed to the spectrum. And then these two plots in each column tell you kind of the sensitivity reach for a given spectrum in beta over h and alpha. For some fixed values of beta over h and alpha, and vice versa.
what are the spectra then, which are, so gamma is a kind of 3-ish, basically. It's around 3, the gamma, the slope of the going up.
Well, it depends, right? So here it's a mix of the two. Yeah, but actually you're right. In most cases it runs through exactly. So
it's basically phase-space kinematics.
Right. So okay, but the main lesson I wanted to draw from this is that if you look at the current experiments, these are EPTA and nanograph, and LIGO would be kind of up on the right, like here. See it, but anyway, so LIGO would be roughly similar to the EPTA nanograph curves, but now shifted to a temperature of 4 × 10⁶ GeV. By the way, these are temperatures, so these are kind of the reading temperatures, so this already gives you information for at which temperature, which phase transition would be detectable.
Are you on the authors of this paper?
No, I'm not.
But because one should really do this exercise assuming that the EPTA signal is real.
Yeah, sure. I mean, this is 2018. It's like
so there's a real signal here in this region?
Yes.
So there's a phase transition of...
No, but the axis frequency or what?
the axis is now already converted to temperature. So
Okay, yeah, then I don't know where in frequency. It's 10 to 7.
Yeah.
So I don't know where it corresponds to temperature.
Anyway, so the main lesson I want to draw from this is that you need small beta over h to be visible at the moment, and you need large alpha. That's kind of so. And both conditions are naturally fulfilled in Copenhagen. And that's where we now get to.
Sorry, remind me, alpha was what?
So alpha is the strength of the phase transition, right?
Yes.
Like the energy released during the phase transition over the radiation. So in supercooled phase transition, alpha is very big, and as you'll see in a second, also beta h is small. So you're exactly going into the regime where you are detectable both by EPTA and nanograph and also by LIGO. Or in order to be detectable by EPTA, nanograph and LIGO, only current experiments or observatories that see something, you have to go into this region.
But the problem of frequency, no? Of course, is very different. You cannot.
No, I mean, I'm saying so.
LIGO and EPTA are very different.
Sure. Now, I mean, this is a general statement. So
sure,
now, of course, you have to adjust the frequency. I mean, these are two different theories.
Since the slope is blue, you cannot have a signal in EPTA and in LIGO.
No, that was my point. I'm saying if you want to see something either in EPTA or in LIGO or in nanograph, you have to go into this regime. Then, of course, you have to adjust the temperature of your phase transition.
The signal cannot span both.
The signal cannot span both. That's not what I wanted to say. Okay, let's now go quickly to the last part.
But that's good on, because the turnaround frequency that the one with the field changes is naturally around the temperature of the phase transition.
Exactly, that's set by the temperature. It's not, I mean, it's set by the temperature of phase times some proportionality factor.
So clearly, if we see a signal at the EPTA, then the spectrum must decay.
Of course, no, and again, this was my point. My point was, now, you want to see something, I mean, say you see something in nanograph, or, well, there is something in nanograph array, or you see something at LIGO, right? Two different cases. In either case, you need a theory with, like, large alpha and small beta h. I mean, in order to produce gravitational waves in phase transitions that can be detected by these observatories. Then, of course, you have to adjust the temperature at which this phase transition takes place accordingly, right? So for LIGO, this would be in the range of 10⁶ to 10⁷ GeV. For EPTA and nanograph, it's more around 10⁻² GeV. So these
2.
10⁻² GeV. That's a bit like that. So again, these would be two different cases, but the lesson I wanted to draw, I wanted to kind of motivate now these very strongly supercooled phase transitions with large alpha and small beta h. I mean, the lesson is really, that's what we'll come to. These are the ones that you can see in current observatories.
So if PTA is correct, we must expect one explanation would be a phase transition around 10 MeV.
10 to the minus 2. Yeah, 10 MeV, exactly. Yeah.
That's nice.
Exactly, so.
Yeah, but that's also unlikely.
What?
That's unlikely. What kind of transition you can have?
Some conformal phase transition.
Like mesons coming.
No, I mean, it can be a dark sector, right? It's
Dark sector.
completely coupled here, so it can be completely coupled sector. So
Yeah.
in principle, I guess there's nothing wrong. With probably there are already like 100 papers about this.
So in the dark matter side.
Yes. Dark sectors.
Dark sector, it's not
Dark
necessarily
conformal
related to.
Yes, but it also has to give a sizable fraction of the matter of the universe, so that the universe wouldn't care. I mean, this dark sector must also contain a sizable fraction of the matter of the universe, otherwise the production would be negligible.
Yes, like dark matter.
Yeah,
Also for dark matter.
Yeah. It has to be a sizable fraction of the matter, otherwise the output of the signal will be bigger.
Yes, probably true. Okay, so so let me just now. So this is the last part. I want to come back to what I started with the Coleman-Weinberg model, and this has been discussed in a very nice way by Witten.
Really? Witten again?
Witten again? Yeah, that's amazing.
In 1981?
Really impressive. Yeah, probably last after his PhD thesis, or maybe still during his PhD thesis, he puts this out. Okay, just to remind you, because it was a long time ago, so the Coleman-Weinberg model was that's a model where you couple a complex scalar to some gauge field. So you have two scalar degrees of freedom and one gauge field degree, one gauge field. So two more degrees of freedom from the gauge field. And then we analyze this in a regime where we can neglect the radiative corrections from the scalars. And this was this regime where the scalar coupling squared is much less than the gauge coupling to the first power. And then we found that the effective potential is given by so it's just a tree-level contribution, and then there was a radiative contribution. Where MA here is the mass of the gauge field in this background of non-zeros that for phi. So phi gets a mass to this gauge field, breaks the gauge symmetry, the mass is given by 2g squared times phi squared. And I kind of wrote this before as kind of lambda effective, so I wrote this before as lambda effective of phi, and this is times phi to the fourth, but then it's more convenient to write that explicitly. And then there is a Flammable correction term, and this depends on the temperature. With this thermal function JB that we calculated as a function of the mass squared and the temperature squared, and the temperature to the first power. So now let's focus on a regime of the potential where MA squared is 2g squared phi squared, that's a function of phi. So for 4 small phi values is much less than the three. This is a region for small phi, this is fulfilled, right? And then for small phi, so if this is fulfilled, this argument is very small, and we can use high temperature expansion of this function that I had already on the netboard before. So we can use this expression. There was a constant term. Squared. So this is relatively weird cubic term, MA cubed over T cubed. And then finally, this term of order MA to the first power over T to the fourth power. Where AB is a constant that I had in the blackboard before, it doesn't matter now so much. Again, good with the higher order terms, but this is where we stop our expansion. So now we can take this and plug this in here. But now you see this doesn't depend on the field, so we can already forget about this term. It's just a constant term. It's times T to the 4, so this doesn't give any non-trivial contribution to the potential. And I will also neglect this term here. Because of these so-called daisy corrections that I didn't really have time to discuss, but they essentially make this term less effective than it seems at first. So let me just neglect this. In the plots that I will show at the end, this is actually taken into account, and you will see kind of what the difference is between taking account or not. The difference is not very big, but it has some effect. So I will neglect this, this, this. So we will just keep these two terms here. And now you see that kind of this term here goes like log over the mass squared. It has the same dependence as this one here. And well, if you work it out, you will see that this exactly cancels this term here, this field dependent term. So the MA is a function of phi, right? This piece is cancelled by this piece. And then, okay, I'll just write it down, and then we can check if you want. What you get is the effective of phi and the temperature in this regime where phi is very small. So for phi much less. So convert this phi much less than T over root 2g. It's given by 3 over 64 phi squared. And a to the fourth power. And a always a function of phi, remember that. Log of t squared over mu tilde squared, mu tilde is what is this? Plus 3 over 24 squared. And mu tilde is just a redefined version of the randomization scale mu. Okay, so you see that kind of the field dependence in the log disappeared because this cancels with this here, and the log now just depends on the temperature. Just a curious feature. And the field dependence is now just in the prefactor. This goes like a to the fourth, phi to the fourth, right? And then there's a term that goes like phi squared times the temperature squared. That's the thermal mass term. So you have a thermal mass term, and this is a quadratic coupling that kind of depends on temperature. So, and what I did also here, so if you were attentive, you noticed that so I have this piece, these two pieces. I forgot about this piece. I didn't forget about this piece actually. I just choose the randomization scale where lambda is 0. So this I can always do. remember lambda was going like, lambda was effectively running like this, right? So you start with a negative lambda here, and then at some point it turns positive. So this was lambda of phi, but it's the same of mu, it's the same running. So I can choose in a randomization scale where lambda is 0. This is what gave us the non-zero minimum for potential. It's like at 0 temperature. Effective of phi. That was essentially because of this random body coupling. Okay, so I choose a RG scale when this is 0, which I can always do, and this is just out of convenience. And then this is really the potential I'm left with.
Is there a natural way after this instance you should adjust the offset of the potential?
What do you mean, the offset?
The cosmological constant.
No, this you have to tune that. At least, well, this is a CC problem. It's if you can come up with a core solution, that would be very explorative. So this is always assumed to be, yeah, this I never really, well, maybe I mentioned at some point, but I mean, always the assumption is that there's a constant here, SC, right? That is adjusted so that the cosmological constant in the minimum at 0 temperature is 0. Right? So this is
you already dropped a constant there.
I dropped a lot of constants here already, exactly. So, well, these constants are temperature dependent.
It's temperature dependent.
So they wouldn't contribute anyway. So but you have to adjust, of course, at 0 temperature, right? You want the CC to be close to 0 at 0 temperature. Okay, so okay, so this is the potential we will work with now, right? This is kind of the Coleman-Weinberg potential. The potential for the Coleman-Weinberg model at non-zero temperature and small phi. I mean, small enough phi. These phi smaller than temperature over root of 2g, where g is the gauge coupling. Okay, so you see that, so this again, this is a quartic coupling, right? This goes like 5 to the 4th. This goes like 5 squared, this is mass 2. So it's a mass term with quartic coupling. And in the limit where the temperature is very small, but this is negative, right? So this is kind of the, so in this situation, what I have a barrier. And this is kind of what I showed already at some point before. This is maybe like just derived in a slightly different way. So I have the thermal mass term which dominates at 275 squared at small field values, and then at some point I have this thermal barrier from this t squared over e to the square term. Then at some point, at even larger field values, at some point, this whole approximation breaks down. So you have to. So this is the first thing I want to check now. So that kind of, because I want to use this approximation to calculate the tunneling rate, I want to check that that the whole barrier is in the regime where this approximation is valid. The regime was kind of this here, right, where t is less than. So this is one thing that you quickly have to check. And just to give an estimate of the barrier, so I set this value into 0. You can see, right? So it's normalized such that for phi equals 0, this potential vanishes. And so I define this the end of the barrier as a point where, again, the effective of phi barrier is 0. Just to give an estimate of where the barrier ends. Probably should really good. I mean, essentially you have to ensure that you tunnel, right, that the release point at which you tunnel is still in the regime where this is valid. The first approximation is good. Okay, so then this is simple to solve. I take this potential, set it to 0, and solve it. And I find that this phi barrier is the you want this to be less than, to believe this regime when this is valid, to be less than t squared over 2g squared, right? 2g. 2. So now that there's a g squared here. Okay, anyway, the point is really just that you see that if this temperature becomes small enough, so if you are a very supercooled regime, this is fulfilled. Right? So as long as your phase transition is sufficiently supercooled, and I will show you in a second, like when that is the case, as long as the phase transition is sufficiently supercooled, the barrier is always in this regime where this approximation to my potential is valid, right? So I can just use, the whole point of this was to justify that I can use this potential here to calculate the bounce action. Because that has a very simple form. Of course, I can do all this analysis exactly like numerically. It's not very difficult either, but because I want to do analytic stuff here. Additional formulas, I want to use this approximation. Okay, again, the upshot is if the phase transition is sufficiently supercooled, so if it takes place at sufficiently low temperatures, if T becomes sufficiently small, then this condition is fulfilled, and I can use this approximation to calculate this approximation to the potential to calculate the bounce action. So now let me just write this as follows. So I write this as so this is just a rewriting now. We call this is a quadricoupling rate. I call this one the effective of T. And this is a mass term. We call it an effective of T. And now is a nice new formula for potential.
It's mass term is squared, right?
So this is just, if you compare this and you know the definition for them, effective and ineffective. So just formula, which is actually derived by Parisi and
without any replica trick.
Without any what trick?
Replica.
Replica, right?
That's what he got our prize for.
Ah, okay.
Some statistical mechanism.
Yeah. So, okay, for this potential, it is no. And Parisi. 1978 showed that now the bounce action for this. And by the way, you can show this. I didn't mention that that the dominant bounces are those three symmetric ones. So not the four symmetric ones, even though the temperature is very low, it's a bit counterintuitive, but the dominant ones are the three symmetric ones. And for the three symmetric ones, the bounce action is given by just a very big numerical factor in front. Let me write like this. There's 4.5 times 6. 4 pi times 6. Then there's this number that I'm not really sure where it comes from. I guess there's some integration that they did. Then it goes like the mass term over effective coupling. mass term squared. It's the root of the mass term squared divided by minus the temperature-dependent effect of core decoupling. This was negative, right? So minus 1, this is positive, divided by the temperature, and that's the symmetric effect. So, okay, so now, because what I want to get at now is to kind of give you a formula for the nucleation temperature and for beta by H. So this is what and then I'll be done, so it won't take much longer. And so now we know the bonus action. And remember, so the tunneling rate was given by, for those three symmetric bubbles, we essentially said we would estimate this prefactor as t to the 4, and then it's minus S3 over T, right? That's the tunneling rate. And now for this for the phase transition to start, that's a definition of Tm. So at Tm, this is roughly equal to the Hubble rate f Tm to the 4th power. Okay, so now we know this side, so we have to still determine this side here. Now, again, I'm aiming for a situation where I have a lot of supercooling, so the nucleation temperature is very small. And in this case, as I've also already mentioned, the energy density that determines the Hubble rate is determined by the kind of the gap between the faults and the trabeculum. That's the situation again. Supercooling, then you have here some energy density, and then the Hubble rate really, for a lot of supercooling, is of order. Can you tell me a bit more? Exactly, it's a prefactor. The Hubble rate is given by. So essentially, there's of the thermal contribution to the energy density, but this you can neglect, and it's roughly given by energy density between the faults and the true vacuum divided by the scale squared. Okay, so that means what we have to determine is kind of this quantity to determine the Hubble rate, and for this quantity we just have to minimize the potential. So this is now, we take the zero temperature potential, roughly at least, and kind of determine the energy density at the minimum. And then this tells us this quantity, right? And then now we'll to speed things up. I will just give you the result, but it's very simple calculation. So you find that, let's call this minimum. You find that energy density effective at 5 minimum. That's approximately this delta rho, the gap, because this is normalized to 0 here, is given by minus 0.17, and this is some constant that arises from a lot of numerical factors times the RG scale, this redefined RG scale to the 4th power.
So is this only for alpha larger than 1?
It's for, exactly. So in all these, like everything I'm doing here is I'm already assuming a lot of supercooling, so very large alpha indeed.
So that you can neglect radiation.
Exactly.
Usually.
So again, I mean, for now I'm just assuming this.
So this really dominates the energy density of the universe.
Exactly. So this is kind of like a CC that now dominates the energy density of the universe. You enter a stage of inflation, and then inflation ends because of the dominance.
And then you have reheating.
Exactly. So then the nucleation temperature is much lower than the critical temperature. Which is also of order the mutility, right? So there's one scale that sets everything, the critical temperature, and the reheating temperature also. and the nucleation temperature is much lower, right? So you hit the critical temperature of water Newton, you cool down for a very long time to some very low nucleation temperature, and then you raise the temperature again to this temperature of water Newton.
Right.
Yeah, but this can only happen before the photosynthesis, no?
Yeah. So I'm not sure what you would do for undergrad.
No, I mean, if you are really big primordial, no, it cannot happen. It will screw up the photosynthesis.
No, but I mean, what do you mean after? So, of course. Yeah, exactly. So if you do it after, it would probably, then you reach a lower temperature, then you get into this temperature, then of course it would screw up things exactly. So, yeah, so for that reason, for undergrad, I'm not sure what you have to do.
But then you have to assume somehow that when you reheat, the reheating temperature is thermalized with photons, etc.
Right.
So do you know if there's so we talked about this, if there's some reheating mechanism like inflation, where the scalar field goes oscillating?
But I mean, here it's just bubble. I mean, the energy initially is stored in the bubble walls, right? And then they collide, and then the thermal plasma is excited, and then it's a very complicated process.
So it's by bubble collision, but then
it's bubble collision and then some kind of thermalization. So I'm not sure this has been actually studied. This process.
Because it seems to be these two different things. One is these bubble collisions, etc., and then the other is this mechanism.
But this is the same thing, right? So I mean, because the energy density is stored in the bubble walls.
Right.
The temperature is very small, but there's a lot of energy stored in the bubble walls. And then once the bubbles collide, and the phase transition completes, this energy kind of is again redistributed into thermal plasma. So that raises.
Okay, I have to think some more.
Okay, so now we have essentially both sides of this relation, right?
So that's it. That you finished there. That's mu to the fourth.
Yeah, mu to the fourth times some coefficient.
This mu is like a randomization scale.
The mu is the randomization scale, but yeah, it's kind of the scale that sets everything, because I kind of chose it to be the scale where the coupling vanishes, and yeah, I guess the intuition is that the coupling vanishes very close to the minimum, so it's kind of, it sets. I mean, this is really fine. Then, like, this is the scale that determines everything, but this RG scale is very close, because I chose it to be where the coupling vanishes. Okay, so now we have everything. So we have analytical expression for this side, analytical expression for this side, and now we can just combine the two. And again, I will just jump straight to the result. Try to check this if you want. And the result is that you have to satisfy the following condition. It's weird. So it goes like this: 44 over g cubed has to be approximately equal to the log of mu to the squared over Tn squared times the log of scale Tn root f 0.7 3 squared.
So this is just this gamma n.
This is exactly this criterion now.
Okay.
Like plugging in this here and the result for the Haber rate at well, essentially at any sufficiently low temperature, because it's dominated by the differences in vacuum energy densities. And then you get this criterion for the nucleation temperature.
So it's a product of two logs.
It's a product of two logs, exactly. So the one log comes from here. Well, I guess you take the log of this and then you
So it's square root of 0.17 divided by what?
By 3. By the way, I get slightly different results for the numerical factors. Somewhat different results for the numerical prefactors than the paper I will show in a few moments. So maybe, yeah, I'm not sure. Either they made a mistake or I made a mistake. But if someone in the audience, if someone watches this and wants to check it and finds who is wrong and who's right, please let me know. Drop me an email. Okay, so let's call this function f of Tn. So just to make it a visual. So essentially, I have to. The idea is now that I pick a gauge coupling, and now I want to determine the nucleation temperature for that gauge coupling. And that's so. You see, the right hand side is independent, so I can just plot it.
So you have to pick a renormalization scale as well.
Yes, exactly. So you pick two scales. You pick the renormalization scale and the gauge coupling. The renormalization scale you just pick first. And this will, because it sets the reading temperature, it sets the frequency of your gravitational waves. That's kind of that choice will determine to which of the gravitational wave experiments you are sensitive to, right? So mu total is of the order Tc, of the order Tb.
Of the FGW.
And then proportion to FGW, so there's some proportional constants in front. So this will determine to which experiment you are sensitive to. So as we said, right, this mu total of order 10 to the 6 would be sensitive to LIGO roughly, and 10 to the minus 2 was to monograph.
But you can determine this by just requiring lambda equals 0, right? You can determine this if you know lambda, if you know the self-coupling constant.
Yeah. Okay, you can also re-express it in terms of lambda. Exactly.
Yes.
So it is.
Okay.
It's just a for this purpose more convenient parameterization.
Okay.
Exactly, the two are related. Okay, so let me just quickly plot this, and then I can show you some. So this is function f of Tn that I defined here, and now here I did it for mu tilde TV. Just as an example, and you see that it goes like this. Just need to give you some idea how it behaves. So it goes like this. This is the function of Tn. So GB. Call this function the function of Tn for a fixed mu tilde, and then this would be 10 to the 4 GeV. This is a logarithmic scale here. 10 to the minus 4 GeV is roughly where the maximum is. 10 to the minus 11 is 1 plus 0 again. Okay, this is the right hand side, and now you have to compare it with the left hand side. So now you have to choose. Some gauge coupling, and then depending on the gauge coupling, this will give you a number. Let's say you get something like 500, so I don't know what G would correspond to, but 400, so you get a line like this, right? This is the right hand side here. Okay, now you can just read off the nucleation temperature, right? So you see, you start from high temperatures, and you the nucleation temperature is now given by the point where these two curves cross, right? This is not much, but now my point is kind of to visualize that now if you make G smaller, this blue curve moves up, and the nucleation temperature goes down. Right? So the smaller G is, the smaller is the nucleation temperature, and the more supercooling you have. Right? That's what you see. And what you also see is that at some point if G becomes too small, the curve is here, and you can never actually satisfy this criterion. So there's a situation where you supercool so much that you never actually do the phase transitions. Okay. And the last thing, I'll show you the last plot I wanted to show is, so now we know how to calculate the nucleation temperature. We know that we get supercooling the smaller the gauge coupling is, the smaller becomes the nucleation temperature and the more supercooling we have. And the final quantity I wanted to calculate is beta H of Tn. So this is Tn, right? This was the quantity that we wanted to be small for the gravitational waves to be strong. Okay, now you can just plug in this expression here and work it out. And what you get is, it goes like 88 over g squared, 1 over log of Tn over mu tilde, all squared. Okay, so this is actually like the main result of this whole section. It tells you that the smaller the nucleation temperature is, the smaller becomes beta OH. Actually, it's a little bit tricky because you have this 1 over g, I just realized, but I mean, I guess if you now re-express it, yeah, I didn't do that, so if you now re-express it, you can get rid of the 1 over g with this expression here, you should still get the same result. So okay, this one makes it a bit less obvious, but the point is, so I guess you have to plug this in here, and then you see that the point is, the smaller the nucleation temperature, the smaller the beta OH.
It's a log dependence. It's not very. It's a log dependence.
It's not very strong, right? But not very strong. But I mean, but because you can kind of supercool a lot if you make the gauge coupling smaller, you still can get down to beta OH of order few. So you can get small beta OH, and then because alpha was given by right, the delta rho of the radiation temperature is over Tn to the fourth becomes very big. Right? So you have the two things that kind of maximize the gravitational wave signal. You have small beta OH, large alpha, and also the ball velocity over the photon, because there's nothing in the plasma to stop the wave.
How do you see that alpha is large here?
Alpha is large. I mean that's straightforward, right? Because it's delta rho over rho radiation, and this is of order Tn to the fourth, right? So if Tn becomes very small, this blows up. Okay, so this was kind of the thing I wanted to show. So my point really is that kind of these Coleman-Weinberg type models with a lot of supercooling phase transitions in these models are the one you can actually currently observe in current gravitational wave experiments. That's kind of why people are interested in them. So later, once VISA comes online, then you can, for example, you could also see much weaker phase transitions in other experiments. But for now, that's really all we have. So that's why people are in particular interested in these models. And yeah, what I didn't have time to talk about was kind of that there is these Coleman-Weinberg models. Remember, we had to set the tree level mass to 0, which some people can find ugly, me including. But there are very nice realizations in nearly conformal models, something I also talked about in my seminar on Wednesday, where this actually comes out naturally, so there's no tuning involved. So you get essentially the same potential as in the Coleman-Weinberg models, but in a natural way without having to tune the mass down to 0 or something. And then there's an interesting connection to 5-dimensional Reynolds syndrome models by the ADCFT duality. Okay, the last plot I want to show now. 2212. 2212. 08085. 5. And we want to look at figure 2. Yeah, it's a very busy plot. So the plot on the right-hand side of figure 2, it's a very busy plot. But this is essentially exactly in this Coleman-Weinberg model. On the y-axis is the gauge coupling, on the x-axis is, they call it M, but I mean, it's really my mu tilde, what I call mu tilde. And then they plot kind of the potential reaches of, the reaches and potential reaches of different gravitational wave observatories. And yeah, it's very busy, so you see like what they put in orange are the present bands. The dominant ones come from nanograph EPTA and IPTA on the left, for small m, 1 mu tilde. And there's a tiny little bit from LIGO Virgo 03 at around 10 to the 8 GeV, 10 to the 7, 10 to the 8 GeV. And then there's also a bound from additional number of degrees of freedom that we can talk about. It's actually also quite constraining at the moment. Yeah, but I mean, so you see that kind of, so LIGO Virgo will increase a lot, so you can probe a lot of this parameter space, and then there are different types of experiments. BT is the ancient telescopes, CB is Cosmic Explorer, there's BT SIGO, D-SIGO, BBO, LISA, and the SKA. And kind of the main point is that you can kind of, with all these experiments, you can essentially probe most of the parameter space of this model. So the philosophy is, it's like Lampos science, right? So the philosophy here is kind of you have no good reason to assume that there's such a model, but okay, you just assume there's such a model, right? Undergoes a phase transition, then it would produce gravitational waves, and then you would detect them. And so if you don't detect these gravitational waves, then at least you know that there's no such theory out there, right? So you will still learn something about the universe. Or maybe you detect something, then
They have a price.
then you have a little price.
So then you can make the translation between this and the conformal field theory.
Exactly, and now they also actually discuss in the second part of the paper, they discuss the safety case. So it is very similar because the potential again is very similar. So
oh, that's really nice. Yeah, that's good.
Okay, thank you very much.
Wow, thank you very much. So we have a full lecture you cannot see here, but
The lecture room is full of people.
Yeah, thank you very much, Benedict, for this very nice set of lectures. Let's stop recording.